And hello, welcome back to YouTube, to our fellow OpenFoamers, to this video. Today we're going to talk about, continue discussing our boundary conditions. So remember last video I was telling you that, the pressure for the solid solid condition here isn't really that important. So, but I mean, for the sake of consistency, we can always do some change dictionary here. And we're going to copy this over, the sphere to oil. I'm going to change it to 1 times 10 to the 5th, just to have a good initial condition for pressure. I mean, just so you know that how this change dictionary actually works. So let's go to sphere, change dictionary dict, and I'm just going to paste it down here. Sphere to oil, and uniform should be 1 times 10 to the 5, 1e5. Okay, that should satisfy it. Okay, so now yeah, question is this: what is the deal with rho? Okay, let's go. What's the deal with rho and PNP-RGH? These three I did not explain too clearly. Of course, one has to deal with density changes. One has to deal with the pressure without the hydrostatic effects. One has to deal with just pressure itself. Okay, so why are they there in the first place? And how do we make these boundary conditions work? So for PNP-RGH, we can actually take a look at system and go to the change dictionary, and we take a look at PNP-RGH. Now, what is PNP-RGH actually? So, and what are these boundary conditions telling you to do? Okay, one says it's a fixed flux pressure, and now as I explained in the last video, fixed flux pressure is the pressure, using PRGH, but in the presence of gravity. So PRGH is the pressure without contribution from the hydrostatic pressure. So for every part of this fluid, the pressure excluding the hydrostatic pressure is uniform at 1 times 10 to the 5, 1 times 10 to the 5th. This is this is exactly what we want. Where is it? Yeah, never mind. Let me see, fixed flux. Yeah, this boundary condition sets the pressure gradient to the provided value such that the flux on the boundary is specified by that velocity boundary condition. And if you take a look here, yes. So again, in here also in OpenFoam.com, in the above example, all boundaries use a boundary condition fixed flux pressure. This boundary condition is used in pressure where zero gradient is generally used. So normally, remember when we do a pimple foam or piezo foam, when we have a wall boundary condition, we usually use zero gradient. But since there's gravity and surface tension in these equations, there needs to be some change here. So this will take into account all those things, especially the gravity, since these are hydrostatic forces. Then why would we have to also define the pressure field? Well, technically you don't really have to define the pressure field. That's why you use this type boundary condition type called calculated. What does calculated do? Calculated boundary condition, as you say here, this boundary condition is not designed to be evaluated. It is assumed that the value is assigned via field assignment and not via a call, blah blah blah. So what it's saying basically is this: the pressure field will be taken from this PRGH field. since we already specified the PRGH, we don't really have to specify the pressure per se. That's why you use this calculated boundary condition. Otherwise, you kind of over specify the system and the simulation will probably crash. Okay, now what then is rho over there for? And we can see that in the change dictionary dict, there is no change to the boundary condition in rho, right? So if we take a look at oil and we take a look at the rho boundary condition, we see that the internal field is all uniform 8,000, 8,000, 8,000. Okay, so what is it trying to say? What it means is that over here, again, the type is all calculated, meaning to say all the values are taken from elsewhere. These are just like placeholder conditions. You don't really have to bother so much. But of course, we can actually change this to 8,000 just to match everything up nicely for the sake of looking good. But your pressure, your densities are all determined elsewhere. Okay. And usually, but okay, let me go and change it first. Yeah, I want to just make it look a bit more symmetric. Don't mind me. Oil to sphere. That's in the P. Oops, sorry. Okay, 1, 2, 3. Nope. And delete this. Okay. All right. Let's me. Yeah, that's more like it. And I go 1, 2, 3, 4. 1, 2, 3, 4, and I'm going to change this to. Oh, shucks. I think I put it in the wrong field. That's me QA. Okay. QA. Okay. I didn't write anything in. Good. Let me go to the row. Yeah. See, VI sphere or VI oil and row. Yeah, so basically, anyway, as I'm doing this, just a thing that why is it here? The reason why it's here is that, you know, in buoyant pimple foam calculations, there is always a need to change the density every now and then, because otherwise there's no natural convection. Okay, so the roll file there is basically to help OpenFoam kind of reconcile, hey, where do I put all this what do you call that? Where do I put all this information for intermediate information for about density? So this is where you actually put it, in the row field. Okay. So there we had 8,000. We just make it 8,000 just for the sake of making everything equal. Okay. We might change the value later to fit whatever we want. But honestly, this isn't so important as much as just to like make it look symmetric. Okay, so anyway, the row here we don't really bother so much. Just for oil is because, I mean, oil will be used more the row will be used more explicitly in the oil boundary condition. So it looks as if we want, I mean, change dictionary is more or less done. All we need to do is to just quickly try and run it and see what's the result. Okay, we can always change it later, and we can always do an all clean and then change the change dictionary if you want to change our boundary conditions. But this is where we normally should change our boundary conditions, just so you know. And hopefully now you kind of get the difference between the P and the BRGH and how to assign boundary conditions for them. So remember, at the walls normally we use 0 gradient for pressure, but because of the gravity that's present, there will be a hydrostatic pressure contribution. Therefore we cannot just use 0 gradient, we have to use fixed flux pressure instead. So that's what how we're going to change the boundary condition. Let's try all run 0 pre. Okay, and this should be able to do our change dictionary. Hopefully things run well and we'll get the expected results we want, which is all the boundary conditions are written correctly into our files. So let's take a look at the not change dictionary oil. Okay, so it looks like again there's a syntax error, and let's take a look at the sphere one. So as always there's a debug, though for the sphere change dictionary, it worked perfectly well. So let's go and take a look at the oil change dictionary just to do a bit of debugging. Alright, so again it's reading the oil change dictionary dict at line 173 and 176. It says there's imbalance brackets and ill-defined primitive entry starting at keyword boundary field ending lines 176. Okay, basically it's all our what do you call it, row file, which is kind of pretty wrong. Okay, so let's just make sure the syntax is right. Okay, so we need to see the syntax. Okay, so normally there will always be this processor boundary or something like that. Okay, oil to sphere. Okay, where is this? Okay, there. Okay, let's look at the syntax. So yeah, I guess you always need an internal field entry. Do you? I doubt so, but yeah, you don't always need an internal field. Oh, there is an internal field entry here, and looks like almost every one of them has an internal field entry. So sure, just to eliminate the source of error, I'll just have an internal field entry there in case the syntax requires it. Internal field. Okay, uniform 8000. Okay, just for the sake of that. And boundary field, I'll need a bracket here. 1, 2, and yep, oil to sphere will be over here, and 1 2 3 4, 1 2 3 4. Okay, let's see whether rerunning change dictionary will help. So oh shucks, I'm a little tired, but okay, let me try. My mind's not working as well, but okay. All run serial pre. Okay, while waiting for that, once the change dictionary is done, of course we'll start needing to specify other things before our simulation can run. One example, of course, is the thermodynamic properties. Okay, good. Now the syntax is right, so it's working perfectly. So you can see that the row dictionary is modified, and let's take a look at cd oil vi row. So you see the internal field, everything is now changed perfectly as per what we want. So even the temperature, you see, all is being changed. Perfect. Change dictionary works as it should work. And now next, okay, let me upload this onto GitHub before I lose track of what's going on. Git commit change dictionary edit and run. So next thing we want to talk about is the thermophysical properties. So normally what we use is this this little thing called chtMultiRegionFoam. Okay, hold on. Let me fast forward. All right, so that's uploaded on Git. Okay, let's see. chtMultiRegionFoam. Yes, usually that is what we kind of need to think about. Okay, so what is there a heater here? Probably haven't removed all the things that I forgot. Okay. Anyway, so chtMultiRegionFoam. Let's take a look at oil. Okay, there's only polymesh here, but what we actually need is a thermophysical properties file. Okay, so let's take a look at the air, bottom air, for example, because that's the fluid things that we need there. So 3 files are here for us to kind of copy and edit. One is called radiation properties, one is called thermophysical properties, one is called turbulence properties. So let's go cpar bottom air, turbulence property, bottom, okay, go into oil. So next thing, cpar bottom air, thermo physical properties, oil, into oil, cpar bottom air. I think last one is radiation properties, and put it into oil. So these are the 3 dictionaries we need to pass over. So what we want to do is take a look at the thermophysical properties. I'll try and go through all the things one at a time. Okay, not CD, VI, thermophysical properties. Okay, so normally the model used is the chtMultiRegionFoam, which I'm highlighting here, and this is for, again, according to this is energy for mixture based on density. So there are a few entries we need to have. Okay, so the mixture, we just leave it as pure mixture. Transport, thermal equation of state. These are all how you want to define your for example, heat capacity. You define it here. This is a constant heat capacity, constant heat of fusion. Of course, you have molecular weight here as well. equation of state is perfect gas, meaning to say it's ideal gas, which is not exactly what we want here. We want something more closely resembling oil. Energy is sensible enthalpy, so we just leave it, okay? But anyway, we see here that you can define the dynamic viscosity, mu, at 1.8 times 10 to the minus 5 in SI units, Prandtl number in 0.7. Okay, so let's say we don't want all this, right? We want something more resembling that of oil. So where I would go is to go to heat transfer, chtMultiRegionFoam, and in the heat exchanger, there is a thermophysical properties file in the constant and porous. And we can take a look at the example file here. So this thermotype, it's probably closer to what we want, because here are actually the coefficients for water. Okay, so the thermotype here is hetero-thermal, pure mixture. The transport is a polynomial. What it means is that it doesn't just give you how to say, mu, which is the dynamic viscosity. You don't need to keep it constant. It can be expressed as a polynomial based on temperature. So what do I mean? Let's take a look here. So this is Boolean-esque, different. Okay, polynomial transport. This is transport package using polynomial functions for mu and kappa. So mu is the dynamic viscosity. It can vary according to temperature. So the polynomial expressions are in as such. So yeah, dynamic viscosity polynomial coefficients. I used to evaluate expression in Pascal seconds, but internally it uses Pascal seconds per kilomole. So that one we can deal with later. But just know that it gives you pretty much the SI units that you want. So this one's for dynamic viscosity, this one's for thermal conductivity. So yeah, we want something like this. It will give us a little bit more flexibility when it comes to this defining our mu and our kappa. So this one actually gives us a lot more flexibility. So you can actually just leave it all the coefficients here as 0 and this as 0.001, and that will just give you a constant mu. Likewise for kappa, because how do I say, yeah, because this is the coefficient for the first one. Let me go and use paint. Okay, right, so let's say we have the thermal conductivity equals to A0 plus A1T plus A2T squared plus dot, 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 dot. Then the last one is A8 T to the 8th. So this is how the polynomial is defined, and the coefficients A1, A2, A0, A1, A2, blah 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 to A8. No, this should be A7. Sorry, A7 T to the 7. Yeah, A7 T to the 7 are defined here. 1, 2, 3, 4, 5, 6, 7, 8. So that's how the things are defined. So you see, they are 8. So it gives you a polynomial up to T to the 7th. That will give you a lot of flexibility to how you want to define your kappa and mu. So for the time being, let me copy all of this over. And I'll just tentatively paste it here first. Because this is what I want. hetero-thermal pure mixture. Now look at the differences. Is instead of constant, in H constant and perfect gas, we have polynomial, H polynomial, and ico polynomial. The rest are all the same. So I can just copy all of this, yep, and paste it here. Okay, this is one of the most versatile ways to ever, to actually define your how the density changes with temperature. So with this, it's very good. And of course, we're not going to use constants for water. We want to use it for some sort of oil, hopefully with all these coefficients predetermined for us, so that we don't have to try to rack our brains around how to find all these numbers. So let me delete the older ones first, and this one as well. So I'm going to hold the D key down, and that will do it. Okay, so this is what we will need to write in for our file. Okay, of course there are other models available. For example, this is the Boussinesq equation. This is an incompressible gas equation of state using Boussinesq approximation as function of temperature only. So again, this is a species class temperature reference, and this will determine the density. Okay, this will determine the density for equation of state purposes. Okay, so for example here, in this equation of state purpose, for this equation of state, the Boussinesq approximation is given. So if you can see, hold on. Yes, Boussinesq approximation is here. So this is how the density will change. It's for defining density. Of course, if you take a look at it, you can basically fit the Boussinesq approximation into a polynomial form, because it's just a first, what do you call it? A linear variation of temperature based on some expansivity. So you get the beta, which is the coefficient of volumetric expansion. Rho naught is the reference density at some temperature T naught. So this is a linear variation. Of course, you can just substitute everything into polynomial. This is the most versatile, as I said before. But if you want something simpler like Boussinesq, by all means go and use it. And how is it being written? You can, instead of using all the things here, you just define rho 0, T0, and beta in here. So rho, you just have one entry. For example, rho 0, T0, and beta. You just key in the values that you want. You get your equation of state. So of course, we want, like I was saying, we want a fairly well defined oil. One of these oils is called Dhalsim, okay, and it's got all the properties that we want over here, from 100 to 400 degrees C. Okay, we will have all of these specification. Okay, we all have all these specifications, and the what do you call it? The coefficients. You see, you have this polynomial coefficients from A0 to A5, or alpha 0 to alpha 5, for a temperature of 100 to 400 degrees C. So this will give you the proper temperature relations for Dhalsim. Unfortunately though, this is of course between 100 and 400 degrees C. So for temperature below that, you may not get the same results. So instead, you can take a look at this saturated liquid property chart, where you have this vapor pressure, which is hardly used in here because it's a single phase, not a two-phase thing. but you have a viscosity as a function of temperature here, specific heat, and thermal conductivity. And you can see the thermal conductivity, it's and even the density. These are pretty linear functions of temperature. And it'll be pretty tempting to use the Boussinesq approximation here. I don't see why not. But yeah. And of course, if you want a molecular weight, you can look at this alpha A, this Dhalsim A. It says the molecular weight is about 324 grams per gram mole. Okay, this is yeah. Though the molecular mass here, it's displayed as 166. So rather than adding the molecular weight of these two chemicals together, and then you get 324, I think you divide by 2, you get about 166. Okay, so I think 166 is of course the better mass to use. Okay, yeah. So yeah, this is the average molecular weight of the mixture. This one is like for every 1 mole of this pair of molecules, you'll be weighing this much, I think. So that's why I think there's a 324 here. Okay, but we just have a mixture and then we say the molecule mass is 166. That's usually better. I can explain a little more next video, but yeah, basically it's taking the average molecular mass of these two molecules and pretending the whole mixture is made out of one kind of molecule, and yeah, so that's how the 166 comes about. I think so. Yeah. All right. Yes. So yeah, it's the average. Dhalsim is made of biphenyl and diphenyl oxide. The average molecular weight of this is 166 because the biphenyl has a molar mass of 154. Okay, so anyway, I'll just put all these into the description below. Okay, so hopefully, yeah, next video we want to talk about actually plugging in some coefficients for this thermophysical properties, and then make sure. I mean, if you want, yeah, you want more. If you want a gas model, you can find it on almost every chtMultiRegionFoam. In the foam tutorials folder, there will be a model for air, including this snappy multi-region heater. But for water or for liquids, it's a little bit harder. But anyway, it's in a chtMultiRegion simple foam. You can find it there, and you can plug in all this polynomial expressions for rho, for CP, HF, etc., etc. We can talk about how to get all these coefficients in, later on. Okay, especially for mu and kappa. Okay, so that's all I have for you for now. So mu and kappa, yeah, they don't use Prandtl number anymore. They use mu and kappa. Yeah, that's all I have for you now. See you in the next video. It's getting really long-winded, and yeah, it's a long video already. But thanks for watching. Thank you very much. See you next time. Bye bye.